So taking a look at this uplifting cool demo, I want to explain the flow of heat. This chemical reaction, very spontaneous, is very endothermic. So what it did was, if you're endothermic, it absorbs energy. And it absorbs energy from the entire environment. So some of the air gave its energy to the chemicals in here. So heat flowed from the air. Now, it's a lot of air in this room, so it didn't feel all of a sudden cold, okay? But more importantly, the water underneath this chemical also gave its heat. Heat was going into the chemicals. So the water was losing heat. If H2O liquid gives off heat, what does it become? If liquid gives off energy, what does it become?
Gas.
That's if it would gain energy. Solid. If you add energy to liquid like a stove, it evaporates, it boils, right? So if liquid gives off heat exothermically, it's becoming H2O solid. And the reason why it's an uplifting demo is because this chemical froze the liquid to the board. The liquid gave its heat exothermically to the chemical who endothermically accepted it. When you have an exchange of heat, someone's giving, someone's accepting. Now it gets confusing if you want to know what the process is. Who is it, exo or endo? Well, we always start with the chemicals. What was responsible for the change of energy in this demo?
Heat.
Like mixing it?
Yeah, well, wasn't it the chemicals I started with? Yeah. Who was responsible for the release of heat exothermically from the torch? The propane and the what? Oxygen. So we would say propane and oxygen created the heat to make everything happen in the gummy bear demonstration. This released heat exothermically. Who was responsible here for the flow of heat is the endothermic chemical change. All right? Energy flowed exothermically from the water, and it was drawn in, okay? So much energy was absorbed by the chemical that it made the surroundings so cold, it froze the water to the board. I know there wasn't flames, and I know it was anticlimactic. I needed like an extra 30 seconds for it to really freeze better, but I know I'd have it before the break, somewhat. So, that's what happened here. So anytime I ask you what happens to temperature change, don't think about how much energy the chemical lost. Think about, did it release heat into the environment? Temperature goes up. Did it absorb energy from the environment? Temperature goes down. Okay? So in any case, real quickly, let's get through this so I want you to get on your labs. Okay, now, is this an endothermic or exothermic?
Exo?
Right, you're going high and going low. Of these two processes, I say processes because one is exothermic, one is endothermic. Which one is exothermic? Which one is exo? Look where the heat is. Which one is exothermic? The first one or the second one?
The first one.
If you exiting heat, you're exothermic. It is this heat that warms the environment. The second one is exothermic. The heat is on the product side. So let's write it. H2O liquid becomes H2O solid, which is lower in energy. This is not a thermometer. I'm sorry, this should say potential energy. Cross that off. I didn't get that. That should say potential energy. Okay. This is, of course, what? If energy is going down and heat's on the product side.
Exo?
Exothermic. Energy's being what? Released or absorbed? Released. Hey, the water had to release its heat to get cold enough to freeze. Okay? Temperature. Now, normally exothermic reactions give off heat. Now, this is a kind of a tricky question because, yes, if it's exothermic, we would say temperature would go up. Liquid's freezing. When you have snowing occurring, it does get warmer. So this, because it's exothermic, we're going to say the temperature is increasing. Why? Because heat's being released. But careful, party people. Careful. If I have just a phase change going on, clearly this liquid's not at the freezing point. So we had to do what? Take the heat away to get to the freezing point. But let's pretend we were exactly at the freezing point. There'd be no change in temperature here, would there? At a phase change, correct? Remember, at a phase change, there's no temperature change? Okay, but because we had water at room temperature, it had to go down to get to the freezing point. Okay, it did so because it released heat. Okay, delta H is negative, right? It's negative, why? Because it's going down. Why is it going down? Because water solid has less potential movement, wiggling in fixed positions, than the liquid that can fly out. Okay, bless you, meant it. Who is more stable? The solid or the liquid?
Solid.
Solids are lower in energy. Is this a chemical or physical change?
Physical.
Physical. Circle it, baby. Okay, now, this arrow is misleading. You kind of think that the heat given off by the water drove the reaction. Actually, the endothermic reaction pulled heat from the water. So what we're going to do here is this. Who are the reactants? Well, this is the endothermic reaction right here. All right? So these reactants go here. I know it's hard to write there, so all I'm going to do is kind of circle those three. And they would go right here. They're the reactants. And who are the products? I'll do another color. These three, it's a lot of them, are the products. Now look at here, party people. Look where the heat is. On the what? Reactant side. These three chemicals require heat to become something new. They have to absorb heat. They start low and they go high. So the reactants, party people, are lower in energy, like photosynthesis. Okay. Because we're going up in energy in here, sorry. Is it endo or exo? No. Endo. Heat is being absorbed or released. If you're being absorbed, that means your heat is in the reactant side like that, yes. Your temperature's doing what? What's the name of this reaction? I called it a very cool demo. I made the water so cold it froze. Okay, so temperature decreases always in an endothermic reaction. And what decreases? The environments. Delta H is going up or going down? Starting low and going high. It's going up, isn't it? Because I have this much potential. Forget the free energy, potential. And I grab energy, now I have even more potential because I absorbed it. So delta H is positive. And who's more stable, the reactants or products?
Reactants.
The reactants, that's why they needed energy. Okay, little question here. Energy absorbed to break bonds, then heat released and forming. So because this is endothermic, is there more energy needed to break the bonds or make new ones? Yes, there's more energy needed to break than form new ones. Overall, it's endothermic. So you'd say more energy. Okay. These last three reactions and you're on to lab. Look at this reaction. Is it exo or endo? I don't have any heat written.
Endo.
You're just guessing. Now listen, I always say forming bonds is what? When we form bonds, aren't bonds stable?
Yes.
So if I have a reaction like this, and I start my reactants, I have to break bonds and then I have to release bonds. Overall, I'm releasing more energy. Why would I release energy to make bonds? Because bonds are a lower energy position. To get low, you have to release it. Now, look at this reaction here. These guys are just coming together, correct? Am I breaking any bonds here? No! But I'm forming a new bond, aren't I?
Yeah.
So I don't really have this. All I'm doing is forming new bonds. Isn't a bonding state a lower energy state?
Yeah.
Yes, forming new bonds is always what? Exothermic. This is exothermic.
I called it.
Let's put the heat in. Where would you put it if it's exothermic? On the product side or reactant side?
Real product.
Product side. Exothermic, exiting. We start with this and we're exiting a product and the heat. The heat makes the environment what?
Hotter.
Yes. So the temperature is what?
I got it.
Increasing. Who is more stable in an exothermic reaction? If you're releasing heat,
Product.
products. That's a bonded product is more stable than unbonded. It's the reason why they make bonds. Here is the opposite. Now, what do we know? Breaking bonds always takes energy. Forming them releases energy. But wait a minute. We're just breaking a bond. After class today, all right? Let's meet at West Hampton Beach, Main Street. We'll just go break stuff. Well, we need energy to break stuff.
Yeah.
We're not doing that, by the way. We'll need energy always to break stuff. So to break bonds, you need energy. We're not forming any new bonds. So we're just breaking bonds. Breaking something stable. To change somebody who is stable takes a lot of energy. Okay? So this is endothermic because you're just breaking bonds. And if it's endo, let's put the energy in. Where would you put the heat if it's endo, if it's absorbing heat? Is it exiting or taking it in?
Taking it in.
Taking it in, it's right here. Temperature's increasing or decreasing? Decreasing, you're using up the energy from the environment to make the environment so cold you could possibly freeze stuff. Products, who is more stable?
Reactant.
The reactant starting low and going high, absolutely. Okay? So that is the new material that is tied to what you have to know. Take out your labs.
Just on the question